Welcome to Circuit Analysis Basics. Today we will be analyzing simple electronic circuits with worked examples, utilizing the following solution methods of Kirchhoff's current law, Kirchhoff's voltage law, current and voltage dividers, as well as superposition. So let's go ahead and get started. For this problem, we will utilize Kirchhoff's current law to calculate the voltage across the 12 kilo ohm resistor in the circuit shown. So let's go ahead and identify our circuit component. Our 12 kilo ohm resistor is going to be our V naught. Now, identifying the rest of the circuit as three parallel branches connected to a common node of a constant independent current source. So it is important to recognize that the voltage across all three resistors is essentially V naught. So utilizing Kirchhoff's current law, we can recognize that our current at our source, we will denote as I1, is equal to the incoming currents of all three branches. And we will label this I2, I3, and I naught. So now that we've got some parameters and our values, let's go ahead and write our equations out. Starting with I1 is equal to I2 plus I3 plus I naught. Now let's go ahead and try to solve for these variables. First, we are able to recognize that I1 is simply our 15 milliamps. So let's go ahead and plug that in. Perfect. Now, how do we solve for the rest of these variables? Well, according to Ohm's law, I is equal to V over R. So we just need the voltage across each one of our resistors. But it's important to note, since these are parallel branches, all of their voltage is going to be the same. So we can denote each one of the voltages across as the same variable. So let's go ahead and write that. So we have our V naught over the first resistance, we'll do 5K, plus V naught again, over our second resistance of 7K, and finally V naught one more time over our resistance of 12K. Now, in order to solve for our voltage across the resistor, we need to find a common denominator and add these fractions together. Well, simply to find a common denominator is the multiplication of all three of these values, which 5K times 7K times 12K is equal to 420 kilo ohms. Now, we need to apply this denominator to each fraction and the associating multiplication across the numerator. So, solving for our first term here, we will have our V naught multiplied by 7 times 12, which gives us 84, over our total denominator of 420. Next, we will have our second term, which is going to be V naught multiplied by 5K times 12, gives us 60, over 420K, plus our final term, which is going to be 5K times 7, which is going to give us 35. V naught over 420K. Now, not to forget that this is an equation, so let's go ahead and bring that other half down. Simplifying these equations, we have 15 milliamps is equal to 84 plus 60 plus 35, that gives us 179 V naught over 420K. Multiplying both sides by 420,000 and then dividing by 179, we are able to determine that our V naught is equal to 35.195 volts. For this problem, we are asked to calculate the voltage across the 3 ohm resistor in this circuit. So, identifying that our voltage across our 3 ohm resistor as V naught, let's go ahead and try to solve. Well, this circuit seems a little complex, so let's try to simplify it. Well, first I see a parallel branch of 2 identical resistors. So let's go ahead and simplify this to an equivalent resistance. Well, 4 ohms in parallel with 4 ohms is half the original value of both resistors. So, omitting this whole branch and writing an equivalent resistance of 2 ohms, we have simplified this circuit enough to be able to start writing some of our equations. Well, we can identify the voltage across all of our other resistances as V4, maybe V5, and V2. Perfect. And we can see that 12 volts is equal to our voltage of V4 plus V5, or V4 plus V2 plus V naught. Also, we are able to identify our currents of I total, maybe I1 and I2. And we can also write that our I total is equal to I1 plus I2. Now that we have simplified the circuit and outlined our variables, let's try to solve. So, looking for our total equivalent resistance, I see that we have our 4 ohm resistor plus our 5 ohm resistor in parallel with our 2 ohm plus our 3 ohm. That gives us a total equivalent resistance of 4 plus 5 in parallel with 5, which is 2.5 ohms. Gives us a total equivalent resistance of 6.5 ohms. Therefore, we can utilize our total resistance given our source voltage to find our total current flowing through the circuit. So, our I total is going to be equal to our voltage applied divided by our equivalent resistance, which gives us 12 divided by 6.5 at 1.85 amps. Now we can also identify that both branches have equivalent resistances, therefore concluding that our I1 and I2 are equivalent as well. So let's go ahead and solve for our voltage drop across the 4 ohm resistor. That gives us V4 equals 1.85 multiplied by 4. That gives us 7.38 volts. Plugging that into our original equation here, we have 12 equals V4, which is 7.38 3/8 plus V2 plus V naught. That gives us V2 plus V naught is equal to 4.615 volts. Now that we know the voltage across this entire branch and the resistance across that entire branch, which is 2 plus 3 ohms, we can find the current of I2 is equal to the voltage, 4.615, divided by the resistance, 5, and that equals 0.923 amps equals I2. Finally, now that we know the current flowing through this resistor and the resistance of V naught, we can finally conclude that our V naught is equal to 3 ohms multiplied by 0.923 amps gives us a voltage of 2.77 volts across the resistor. For this problem, we are asked to calculate the current passing through the 2 kilo ohm resistor in the circuit. It is important to identify that the current flowing through the 2 kilo ohm resistor is also flowing through the 8 kilo ohm resistor, and that this circuit is a current divider problem. So let's solve. Labeling our source current as IT and our branch currents as I1 and I2. The equation for solving this is as follows. I2 is equal to the total incoming current, IT, multiplied by the total resistance of the opposite branch you are evaluating. This will be 12 kilo ohms, divided by the total resistance of all branches. That gives us 12K plus 8K plus 2K. Simplifying and replacing our unknown variables of IT as 6 milli multiplied by 12K, all divided by 22K. This gives us a I2 of 3.27 milliamps flowing through our 2 kilo ohm resistor. For this problem, we will need to calculate the current passing through the 6 kilo ohm resistor for the circuit. Now, upon inspection, I see that we have 2 voltage sources. Therefore, we will need to utilize superposition to solve. So, closing out one of our sources with a shorted wire, let's go ahead and solve this side, and then we will do the same for the other source. Well, this seems to be a simple current divider problem in which we need to find our I naught flowing through our 6 kilo ohm resistor. And we can label the total current flowing from the source as IT. Well, in order to find IT, we need to find our equivalent total resistance of the circuit. And this is going to be equal to 8,000 plus our parallel resistance of 6K and 4K. Solving, we are able to find that our total equivalent resistance is 10.4 kilo ohms. Therefore, we can plug this in to our Ohm's law to find that IT is equal to our voltage supplied, which is 12 volts, divided by our total resistance of 10.4 kilo ohms. We can find that our IT is equal to 1.15 milliamps. Now, if you remember from the previous problem, our equation for solving a current divider is as follows. The current of the branch we are looking at is equal to the total incoming current IT multiplied by the resistance value of the opposite branch, which is going to be 4K, divided by the total resistance of both branches, which is going to be 6,000 plus 4,000, gives us 10K. Solving for our variable of IT and the rest of the fraction, we are able to conclude that for our 12-volt source, our I naught is equal to 4.6 milliamps. Perfect. Now, let's start from the beginning, and this time we will be canceling out our 12-volt source in order to solve for the other side. So in the same approach, we have our current total of the source IT on this side of the source. Therefore, we need to find our total equivalent resistance again, which we can solve for as RT equals 4,000 plus 8K in parallel with 6K. That gives us a total equivalent resistance of 7.43 kiloohms. Utilizing the total equivalent resistance, we can then find our IT using Ohm's law of 6 volts divided by 7.43 kiloohms. We can conclude that our total inflowing current of the circuit is going to be 1.18 milliamps. Therefore, just like the other current divider problem, for this configuration, we will have an I naught is equal to our IT multiplied by the total equivalent resistance of the opposite branch, which is 8 kiloohms, over the total resistance of both branches, which is 14 kiloohms. Plugging in our variable and solving, this gives us an I/O of 0.674 milliamps. And we can go ahead and write that up here. 674. Finally, to find the total flowing current, we need to add up both IOs from the separate configurations to determine the total flowing current. And that is going to be 4.60 milliamps plus 0.674 milliamps. That gives us 5.27 milliamps flowing through the 6 kiloohm resistor in this circuit.